Pythagorean theorem is basically a relationship between the three sides of a right angle triangle. And you cannot use a Pythagorean theorem unless you have a right angle triangle. So you want to be very careful to look for an indication that there is such a thing as a 90-degree angle in the corner. Otherwise, it will not work. Now, the preference for Pythagorean theorem is not always to use A's and B's and C's or D's and E's and F's, but to know the general language of the sides in a right angle triangle. For example, most of you already know that the longest side in a right angle triangle is called the hypotenuse. And the hypotenuse is always the side that is across from the right angle. The other two sides are called legs, and they are the shorter sides in the right angle triangle. The relationship that you can write for any right angle triangle is as follows. It's always going to be the length of a leg squared plus the length of the other leg squared will always equal the hypotenuse squared. And with that formula, you can always find a third side if you know two other lengths. If you know a leg and a leg, you can find the hypotenuse. If you know a hypotenuse and a leg, you can find the other leg. The relationship is that the length of the leg squared plus the length of the other leg squared is always equal to the hypotenuse squared. Let's show this with different diagrams. So sometimes you'll have triangles with actual letters on them. For example, the classic way that most students are taught Pythagorean theorem. I don't particularly care for this way because it's limiting, but it still works. A right angle triangle with a right angle at C. Put a C on that vertex and an A and B on the other vertices. You will get a relationship that says, if I follow the rules, across from angle C is side little c, across from angle B is side little b, and across from angle A is side little a. The law states that the length of the leg plus the length of the leg is going to squared is going to equal the length of the hypotenuse. So the length of the leg, a squared, one leg, plus b squared, the second leg, equals the hypotenuse squared. A squared plus b squared equals c squared. That is probably the most common way the Pythagorean theorem is taught. But again, I find it limiting because that only works if the hypotenuse is side C. What if some joker, namely me, gives you a different triangle, puts the letters on there differently? For example, it puts the right angle at B. This triangle then would be, the side across from angle B would be little b. And to write the proper Pythagorean theorem for this triangle would not work with a squared, b squared plus c squared. It would have to be, for this one, the leg, which is a squared, plus the second leg, c squared, equals the hypotenuse of b squared. So again, if you stick with only this diagram for Pythagorean theorem, you are not going to be able to solve some of the diagrams that have letters on different sides. So branch out, memorize the length of the leg, the short leg squared, equals the hypotenuse squared, and you will be able to do any question that you're given. Okay, here we go. I'm going to give you a formula, or a diagram, I guess, with a P and a Q and an R. Q is the hypotenuse. We'll say R is the up and down. P is along the bottom. For this particular triangle, you can write Pythagorean theorem in 3 different ways. You could say the leg P squared plus the leg R squared equals the hypotenuse of Q squared. That's perfectly perfect. If you want to write the equation and solve it for R, let's just say you're trying to solve for the leg of R, you could write it differently. You could say that the length of the leg squared for R is going to equal the hypotenuse squared minus the other leg squared. That's one way to write it. Notice that the Q, or the hypotenuse, must always come first because it's the biggest side. If you want to solve for P, then you would do a similar rearrangement and say that Q squared minus R squared would equal P squared. Basically, however, if you have this one formula down, the sum of the legs squared, each leg squared equals the square of the hypotenuse, that will allow you to rearrange to solve any side of any right angle triangle. Here's an example of 2 fairly easy questions. Say you had a right angle triangle where you were given both legs. One leg was 9, one leg was 10. And there's the indicator that it's a right angle triangle. And you were asked to solve for the hypotenuse of x. So what I'm always looking for is one indication that you know the proper equation for this particular triangle. So I would say that you should write down something similar to this. 9 squared, which is the leg, plus the other leg squared, which is 10, equals the hypotenuse squared, x squared. From there, if you want to do the rest in your calculator, that's okay. I'm going to show the steps. 9 squared is 81, plus 100, 10 squared is 100. So you get x squared equals 181. Now if you look at that number, that's not at all reasonable. X can't be 181. The last step is to take the square root of that number, the square root of 181, which works out to be 13.5 when you round the nearest tenths. If it was centimeters, it'd be centimeters. If it was millimeters, it'd be millimeters. If it's units, it's just units. And that is the length of the hypotenuse. Note, it's longer than either of the 2 legs. The other kind of question you could potentially see, really only 2 kinds in the whole section, hopefully your triangles are better than mine, is if you get given the hypotenuse, 21.7, and you're given one of the legs, notice it's not very well to scale, 9.3, and you're asked to find the other leg. I would write the equation as y squared plus 9.3 squared equals 21.7 squared. Now to solve for y, you've got to get rid of the 9.3. Maybe you're going to rearrange first. Maybe you're going to rearrange second. Let's say we rearrange second. So 9.3 times 9.3, get out your calculator, 86.49, 21.7 squared, 470.89. Now you've got to rearrange. Get your letters on one side, numbers on the other. So you got to do 470. And again, if you're comfortable with your calculator, however, you can do this probably all in one step. Bottom line, you want to find out what the square root of 384.4 is to get the value for y. So you plug that into your calculator, and the answer you're going to get is going to be rounded, let's just say the nearest tenths, since the question was in tenths. So the square root of 400 is 20, so it's going to be less than that. Works out to be 19.6 units, whatever it happens to be. And when you look at your diagram, That answer is very reasonable because the hypotenuse of the diagram is 21.7, so the leg has to be less than that. 19.6 seems to be quite reasonable. Those two questions are fairly normal. Like all concepts, you can start to add some questions that are a little bit more comprehensive, perhaps a little bit more dicey. I'm going to draw an isosceles right-angled triangle. Isosceles right-angled triangle has two equal sides. I'm going to label these sides as x, and the hypotenuse is 30. Now if it's your job to solve for the legs, a length of a leg, or maybe the whole perimeter of the whole figure, you're first of all going to have to figure out the value of x. So you start with the basic principle of Pythagoras, which is the short side squared plus the other short side squared, the leg squared plus the leg squared equals the hypotenuse squared. Now from there you know you can do 30 squared and get 900. The key to the question is knowing from before, when you add an x squared and an x squared, you're going to get 2x squared. Our job is to solve for x. We want to get the x by itself. So the first thing you're going to do in that step is to eliminate the 2. You're going to divide both sides by 2 to get rid of the coefficient. So you're going to be left with x squared equals 450. And once you get it narrowed down to that step, it's like any other. Take the square root of 450, and that will give you the dimension of x. X is going to equal 21.2. So the key to the question, way back in the beginning, is you need to remember that the coefficient in front of an x squared is really a 1. When you add them together, you get a 2. And then, of course, you need to get rid of that 2 because you want to solve for x. And once you know the value of x, you could do many things. Perhaps you would be asked to find, say, the perimeter. Perimeter of a triangle is going to be x plus 30, or 21.2 plus 21.2 plus 30, and get your answer from there. So 42, 72.4. If it was in centimeters, it would be in centimeters. If it was in meters, and so on. So the applications are going to be find the length you're missing, and then either find a perimeter, find an area, find the cost of fencing, all the things that go on and make the question an extra step. Speaking of application type questions, if you had a rectangle, and don't forget rectangles and squares by definition are four-sided quadrilaterals where all the corners are 90s. So right away you should be thinking, if you've got a 90, you could very easily have a right-angled triangle by drawing a diagonal. And now you've got a right-angled triangle, and you have two legs, and you have a hypotenuse. So a very typical question you will see in this section will be something that requires you to apply algebra and Pythagoras together. For example, you might be told that a rectangular park has a length that's twice as long as its width. So the length is twice as long as the width. So now we're into algebra. We're into representing lengths with letters. And you might also be told that the diagonal say, for example, is 20 meters. Find the perimeter of this rectangular park. That's a very typical question. So you start with what you know. The diagonal is 20.
there's our hypotenuse. Now the length is twice as long as the width. So our width, the shortest side, we'll call that x, and our length is twice as long. So if the length was 5, if the width was 5, the length would be 10. If the width was 8, the length would be 16. If the width is x, the length is going to be 2x. And now I have information that I can use to write a relationship. I have only one letter, which is ideal, and I have one number. I can do this calculation now. First of all, Pythagorean theorem states that the leg squared plus the other leg squared equals the hypotenuse squared. The entire key to the success of the question will always be that you recognize that the leg has to be squared. With a 2, squaring a 2 is not hard. You get a 4. Squaring a 3, you get a 9. Squaring a 4, you get a 16. Squaring a 5, you get a 25, etc. So you must show the steps to get this right. X squared is x squared. 2x squared becomes 4x squared when you square it out. And 20 times 20 is 400. Now your next line is going to be the sum of 1x squared and 4x squared. So 5x squared equals 400. So x squared is going to equal 400 divided by 5. You want to get rid of the 5 on both sides. So it's going to equal 80. Now, obviously the length and the width cannot be 80. You have to take the square root to get down to the final answer. The square root of 80 is going to equal 8.9. From that, we need to go back and answer the question. What was the perimeter? Well, we have perimeter of the whole field, not what I've traced in yellow, but the whole field. You would have, the perimeter would be x plus 2x plus x plus 2x. Outside edges.
which is a grand total of 6 x's. Then you go off to your calculator and you type in 6 times 8.9 to get your answer. And this answer is going to be the sum of all the sides, 53.4. Therefore, the perimeter, if it was in meters originally, would be 53.4 meters. Let's backtrack for a second. You're going to be told a relationship between the lengths of the sides. Maybe one side is 3 times as long. Maybe one side is 4 times as long. You need to make up that original equation using a leg, which is on next to the right angle, and the other leg next to the right angle equals the hypotenuse squared to get the final answer. Special cases for right-angled triangles, something you may have learned something about in a previous life. The 3, 4, 5 triangle is pretty darn common, used in a lot of applications, especially in construction. Backtrack for a second why it's a good triangle. The leg squared plus the leg squared equals the hypotenuse squared. So 9 plus 16, 25 certainly does equal 25. Since the left side equals the right side, these dimensions of 3 and 4 and 5 must therefore be a right angle triangle. If I give you another one,
say this time, grossly not to scale here, but say we have a right angle triangle here. We have a 5, an 11, and a 13. We want to know, is this a correct triangle? A leg squared plus a leg squared, does it equal the hypotenuse squared? 5 squared is 25, 11 squared is 121. Add them together and you get 646. Does that equal 13 squared, which is 169? Clearly it does not. So what does that tell us? It tells us that the angle inside the triangle is not a 90-degree angle. That was incorrect to mark because it's not a right angle triangle. And you can say that by mathematically proving that the sum of the squares of the legs did not equal the square of the hypotenuse. If I was to change that triangle to 5, 12, and 13, another very common triangle, then you would get 5 squared plus 12 squared, 25 plus 144, and that does equal 13 squared, which is 169. Therefore, this is a right angle triangle, and I can mark it as such with a square in the corner. Therefore, you will always be able to tell if a triangle is square based on the math of the relationship of the legs within the triangle compared to the hypotenuse. A little application you may not know. If you're trying to put up a wall, you want it to be square with the floor, and all you have is a measuring tape, you can do that. You can put your wall up perfectly perpendicular to the floor if you use an application of Pythagoras. So on your floor, if you were to count out 3 inches, or some multiple of 3, like 6 or 9 or whatever, and you were to count up your wall 4 inches, and then set your measuring tape on the end to the end, when that measuring tape reads exactly 5 inches, then you know that your wall that you're putting up will be perpendicular to your floor. They will be at a 90. 3 inches out, 4 inches up, and then 5 inches from end to end, then you know you have a perfectly square corner and your wall and floor are perpendicular. Also, if you want to know if 4 walls, if you have a room that's square, you can always measure the lengths of the diagonals. If the diagonal this way is equal to the diagonal that way, then the corners must be square and the room must have perpendicular walls.